Hi, I'm Larry White, and I'm an electronics engineer here at Crane. And today we're going to be exploring the electromagnetic spectrum. I work with a team here in the Spectrum Warfare Systems Department. And one of the things we do is test and design equipment that helps our ships find objects in the sky and on the ocean's surface. These objects can be anything from a jet airplane to a warship. It can even detect a flock of birds in the sky hundreds of kilometers away. We're able to do this by using a technology called radar. So what does radar mean? Radar is an abbreviation for radio detection and ranging. Ranging is the word that describes how near or far away something is. It's range. Because we can't always be on the ship to work on the equipment, we've created a very large room where we conduct experiments. This room behind me is called an anechoic chamber. An anechoic chamber is a special room where there are no reflections. We're going to go inside in a minute, but first let's talk a little about the electromagnetic spectrum. The electromagnetic spectrum is a place where radio waves, microwaves, infrared waves, and many other types of waves can be found. One specific section of the spectrum contains a collection of waves called radio waves. All radio waves are found outside of what we refer to as the visible spectrum, or what you can see with your eye without help. This is because the radio waves have longer wavelengths than visible light. Radar technology uses these waves to detect distant objects. Every day we depend on these collections, or what we call bands of radio waves, to help us do things many of us take for granted. For example, the microwave band is what you use to heat up your food in the microwave oven. Another type of radio band is what allows you to connect to a web page on your laptop computer without any cables. Most often you'll hear this talked about in terms of your wireless network that many of you have in your homes and schools. When we talk about radio waves, we often discuss their width, or what we call wavelength. While you can't actually see a radio wave, we can imagine and visualize them around us every day. The smallest radio wave has a wavelength about the width of your thumbnail. And the largest radio wave is much larger than the width of our planet. Can you visualize a radio wave that big? Although I said a single radio wave can be as wide as our planet, most objects that use radio waves to enhance our everyday life, like a cellular phone, microwave oven, or satellite television signal, are fairly small, anywhere from about 1 to 50 centimeters wide. Okay, I promised you we'd go inside our testing room, the anechoic chamber. So come on, let's take a look. So, here we are. Did you notice how the sound of my voice changed when we moved from outside to inside the anechoic chamber? We use the word anechoic to describe certain properties that this room has. The most important property is that the room be able to absorb and keep out radio waves that might interfere with our tests. When many people think of an anechoic chamber, they might think in terms of sound waves and eliminating echoes caused by sounds. But what exactly is an echo? An echo is a wave that bounces off of one or more surfaces. While the chamber eliminates sound echoes by absorbing sound waves, it also prevents any other type of wave from bouncing or creating an echo. It's important to prevent echoes because any kind of wave echo interferes with our ability to accurately and scientifically measure and study the radar waves in our chamber. Let's take a look at the material we use. This entire room, 100 feet long and 30 feet high, is coated with sponge-like spiked foam pieces. I'm holding a piece in my hand. Can you see that it's pyramid-shaped with a wedge tip and that each is a different length? The tips are made from one of the most common elements on Earth, carbon. We use carbon because it is especially useful for absorbing the radio waves. All of these pieces are attached in a very specific pattern, named for the famous Russian mathematician Chebyshev. One of the reasons we use the Chebyshev pattern is because the different lengths help the pyramids capture and absorb any waves from the electromagnetic spectrum that are present in the chamber. When we first came inside the chamber, did you notice at the far end, behind me, is a piece of technology mounted up high? This technology is called an antenna. We use antennas to send out all kinds of waves, including radar waves. These antennas not only send out the radar waves, but they also receive them back, after they have bounced off a surface. The antennas help us to detect how far away objects are, and even what type of object the wave has encountered. This is important because it helps us identify where the bad guys are. When the antenna is sending out radio waves, it's called a transmitter. And when it is receiving radio waves, we call it, are you ready for this? A receiver. I bet you figured that one out on your own. So we have a transmitter for creating the wave, and we have a receiver for detecting the bounced or reflected wave. Did you pick up that an antenna can function as both a transmitter and a receiver? Out in the ocean, or here in our chamber, a radar wave is sent from the transmitter. It travels at an incredible speed, 300 million meters per second. Does that number sound familiar? You may already know that 300 million meters per second is the speed of light. As a radar wave travels across the ocean and through the atmosphere, it bounces off of any solid objects it encounters. After the wave bounces or reflects off an object, it returns to us and our antenna captures it and its unique characteristics. This information, including the amount of time it takes for the wave to reflect back to us, is fed into a computer. With this information, or data, we can determine many of the object's properties, including how far away the object is. The computer uses a formula to answer the question, how far away is this object? The formula is one that you can use in your classroom and is defined as distance is equal to the speed of the traveling radar wave multiplied by the amount of time it takes the wave to return to the receiver. Distance equals speed multiplied by time. You have to divide this total distance by 2 since the wave travels from the ship to the object and then back. Halfway represents the distance from the ship to the object. The computer stores information on all the objects it receives a bounce from, and by comparing a new radar wave with those it has already identified, it is able to make an accurate prediction about what the object is. Now that you know about radio waves, radar, wavelength, and echoes, I have a problem for everyone to work on. You might want to have a pencil and paper ready to write down some numbers. Suppose we are out on the ocean and our ship transmits a radar wave. This radar wave bounces off of a fighter jet far away, and then the wave returns to the radio antenna or receiver on our ship. If the radar wave is traveling at 300 million meters per second and it took the radar wave 0.005 seconds total to reach the fighter jet, bounce off and return to our receiver on the ship, can you work together to determine how far away the fighter jet is? Take your time and I'll be back in just a moment to see how you did. Well, what did your class come up with? Did you say 750,000 meters? If you did, you are correct. You might have calculated 1,500,000 meters, but it is important to remember that the radar wave travels to the fighter jet and back to our ship. So dividing the total distance by 2, which represents half the distance the wave travels, will give you the correct answer. Thank you for allowing me into your classroom to teach you a little about radio waves and echoes. The next time you use your cell phone to send a text message or a microwave oven to make popcorn, stop and think for a moment about those radio waves and how they not only help make your life more convenient, but also remember how they help keep our country a safer place to live.